Hi, can you hear me? Hi. Okay. Okay. So before we start, any questions? Okay. So yeah. So sorry about the exam. So I don't know what happened. Okay, someone else said the exam, and I don't know who was taking the decisions and so on. But anyway, so if you have any midterm concerns, and you want to talk about it, you can talk. We can talk after the class. Okay. Uh, and Yeah, okay, so I'll start the lecture now. Oh, okay, so we'll continue with what we were doing last time. So, uh, so in the last lecture, we saw what a gradient is. It's one of the most important quantities that in the class in general in mathematics. So it's built out of these partial derivatives of a function. Okay, so if you have f, you write this vector which is made out of all these partial derivatives. Okay, so fx, fy, fz, and so on. If it's a function of x, y, z, you collect all these partial derivatives and put them as a vector. Okay, there are these numbers that you get, and you at every point. Okay, at any point in the space, you compute the derivatives, and using those derivatives, you make a vector, and that vector is called the gradient vector. Okay, it's written as del f or nabla f, or the gradient of f. Okay, so that's what a gradient is. And yeah, so one main important property is that if you want, you can use gradients to compute the directional derivatives. Okay, so the directional derivative along any unit vector u is just the dot product of the gradient with that unit vector. Okay, so it's a dot product. So what does that tell you? So that tells you a lot. So that means that the maximum directional derivative or the maximum rate of change that you can get is equal in magnitude uh, to just the max. So gradient dot f. So gradient dot u is nothing but magnitude of gradient times u is of as a unit vector, so times cosine theta. So the maximum you can get for the directional derivative is, so the max you can get is just, because cosine theta can be at most 1, so the max you can get is the magnitude of the gradient vector. Okay, so the maximum amount of directional derivative you can get is the magnitude of the gradient vector. And when can you get that? So the direction in which you can get is when cosine theta equals 0. That means it's the direction of the gradient vector. Okay, that's what you mean by the rapid increase or the direction of steepest descent. Okay, so along the direction of the gradient vector, you'll have the maximum rate of increase, which is equal to the magnitude of the gradient. Okay, so that's one important property of the gradient vector. Another important property is that because of this uh, information, that it increases the maximum along the gradient and perpendicular to the gradient when cosine theta is 0, perpendicular to the gradient, it doesn't change. That means the derivative is 0. That's why the gradient vector is perpendicular to the, or the normal to the level surfaces or the level curves. Okay, so that's another important information about the gradient vector. Okay, so we saw how this fact that the gradient vector is perpendicular to the normal surfaces and normal curve, to the level surfaces or the level curves can be used to compute informations like the tangent lines and tangent planes to the level curves or the level surfaces. Okay, so this is very important information. So this is this whole thing is the geometric interpretation of the uh, gradient vector. And for algebraic purposes, to compute things, it's very simple. So it's just this formula, right? You just compute the uh, derivatives. So that's why when you do anything algebraic, if you do any manipulations, it's basically derivatives, information about the derivatives. So all the properties of the gradient will be the same thing like the properties of the derivative. Okay, so that's so this is something that you should know. So please focus on try to understand all these properties, okay, of the gradient. As I said, this property that the gradient direction geometrically gives you the maximum rate of increase, or the direction in which the function changes the most, is a really important uh, idea in mathematics. Okay, so let's solve one problem. So the question is, find the equation of tangent to some surface. So there's some surface and you want to find the equation of the tangent. So what will we do? Can you tell me what you would do to find the equation of a tangent? Yeah, so let's see. So we have, like, we don't know, there's some surface. Okay, that maybe not. So there is some surface. And we want to find the equation of the tangent here. And as we said, the gradient vector is perpendicular to the tangent. So we have to find the gradient vector. So gradient vector of what function? So what is the function? Can you tell me? The gradient vector which defines the surface, right? So the surface is defined by this equation. So x cosine y minus y exponential x equal minus z equals 0. So I can write the surface as the same, this is the same thing as this equation. Now find the gradient of this. So f is this function. So gradient f, can you tell me what the gradient f is? The derivative with respect to x is nothing but cosine y minus y exponential x. Derivative with respect to y is nothing but minus x cosine y, x sine y minus exponential x. And the derivative with respect to z is just 1. Okay, so this is the gradient. So if you, and the point is 0, 0, 0. So what would you get if I substitute? So cosine 0 is 1, sine 0 is 0, this is minus 1, and this is, sorry, this is minus 1 here. Derivative of minus c is minus 1. Okay, so this is the gradient. Okay, so next, so can you tell me what is the equation now? Right? So we use the property that the gradient vector is perpendicular to any vector in the plane. So that gives you x minus x0 times this fx plus y minus y0 times this fy plus z minus z0 times fz equals 0. So that's the equation, right? So fx, fy, fz is the gradient vector. It's perpendicular to this vector from x0 to x, that any vector in the plane. So x minus x0, y minus y0, and z minus z0 will give you the vector in the plane. Fx, fy, fc is perpendicular to the vector. So that's why if you take the dot product, you get this equation. So let's see what you get. So x minus 0 times 1 plus y minus 0 times minus 1 plus z minus 0 times minus 1 equals 0. Okay, so if you simplify that, you get x minus y minus z equals 0. Okay, is that clear? So yeah, okay. So that your textbook kind of gives you a formula for everything. I'm just writing. So for instance, it deals with surfaces like this. Z equals f of x. It gives you a different formula, but I don't want you to remember too many formulas. If you, it's easy to just, this equation is nothing but this equation, right? Just subtract z and you get different equation, and then you do whatever we did for just any surface of f of x y z equals 0. Okay, so you don't need to write a different formula for surfaces like this. Just write it in terms of a function, which is this equation equals 0, x cosine y minus y exponential x minus z equals 0. Then use the fact that this gradient is perpendicular to the surface. That means the gradient will be perpendicular to the tangent vectors. So that's why the tangent plane is defined by an equation like this. Questions on this? Okay, so let me move on. So the next kind of ideas are about estimating making some estimations. So you might have seen something like this in for derivatives. So we can use ideas about derivatives to slightly approximate compute some values of the functions. If yeah, sometimes it's easy to just approximate than computing the exact value. So some information that you'll use, as I said, this is one of the most important formula. The change in f will be, so to get the change in f, if you move from this point to some other point, delta x and delta y, from here to here. So this is say x0, y0, and you change to x0 plus delta x, y0 plus delta y. That's a point. So you want to compute the change of f, you can do it by going along x-axis and then going along y-axis. Okay, to compute the change as you move from x-axis, that would be fx delta x, and you compute the change when you move along from along y-axis. That gives you fy delta y. So okay, so that's why this is approximately what you get for the change in f. So this is not exact, this is approximate because there are some other higher order terms, but this is essentially what you get. Okay, so similarly, if you have three variables, you change it along x, change along y, and change along z without changing other coordinates. You get this formula. It's very similar to two. So there's always like two variables and three variables. We'll be doing both simultaneously. Here, if it is just function of x and y, and next if you're a function of x, y, and z. And as I said, this you can think of this quantity fx, fy, fz times delta x, delta y, delta z can be thought of as this fx, fy, fz is a gradient vector. So it's the gradient times the vector delta x, delta y, delta z is nothing but the delta of, you can think of it as the delta of the vector r, the position vector. So that's why delta f is nothing but the gradient f dotted with delta r. And delta r is the vector change. This delta r is this vector. This is the delta r vector. This is. You can see that that vector is nothing but the direction. So this is the unit direction. This is u. So the direction times the magnitude of that vector. So delta s is the magnitude of that vector. So you can write it as the direction times the magnitude of the vector. So that's why delta f will turns out to be the gradient times u delta s. Okay, so these are some formulas that we'll use to estimate the changes in f. Okay, so again, so it looks like a lot, but it's not really. It's essentially most of the formulas that you'll see follows from something like this. Okay, so it's to compute the change in f, we do by moving along axes. And as I said, this is the base for computing these things, the base for computing is essentially, if you want to do chain rule, you divide by delta something and take the limit, you get the chain rule. So all of these are following from this formulas like this, just basically this formula. So it's really, really important that you understand this. Okay, so now let's solve an example. So there's this function f of xyz, and it's changing. So you start at a point 0, 1, 0, and you're moving towards 2, 2, negative 2. Okay, this is P0, and you're moving in this direction. And you just moved 0.1 units, not so much. You just moved 0.1 units in this direction. Um, so can you tell me how much will the function change? Okay. So can you guys tell me what you would do to compute how much the function changes? Okay, yeah. So this vector. So can you tell me what u is? Yeah, u is this vector. Uh, so which is, yeah, so P0 to P1, what is this vector, the total vector? Right, so just subtract the coordinates, it's just 2, 1, and negative 2. Okay, so what is the unit vector along this direction? Just divide by the magnitude. So magnitude of P0, P1 is square root of 2 squared plus 1 squared plus minus 2 squared, right? So that's 3. So 3 is the magnitude. So the unit vector is nothing but 2 over 3, 1 over 3, and minus 2 over 3. Okay. So that's what you're moving. So that means you move. So where did you move? So you started with P0 and you're moving to P0 plus, you're moving 0.1 unit. So that means you're moving to P0 plus 0.1 times U. Okay, this is where you moved. Okay, now you want to compute the change of the value of the function. So what would you do in like normally if you really want to compute the change, what would you do? Okay, so before gradient, you would just want to compute the values of the function at these 2 points, right? This one point, compute the value of the function at this point, compute the value of the function at this point, and subtract the values. If you want to get the exact change, right? So did you guys, so if you want to get the exact change, compute exact. If you want the exact change, is nothing but compute f at p0 plus 0.1 u minus f at p0. So this will give you the exact, the change. Okay, but computing these numbers, like you have all these signs and products and so on. So these so computing these numbers is like not that nice. You don't want to compute all these. You would need a calculator to do all these things. But let's see how do you do it with so approximations. So if you do want approximations, let's see how do you get that. So delta f, the change in f is, as I said, will be the gradient times the change. So the change vector is 0.1 u. Okay. So this will be the approximately the change. Exact change is something that you would want, you can compute using a calculator, but this delta f approximately would be the gradient times the change, which is 0.1 u. Okay, so let's compute. So can you tell me what the gradient is? Derivative with respect to x is nothing but cosine x with y is nothing but sine x plus 2z, with z is 2y. Okay, let me write it here. The gradient vector turns out to be just y cosine x. Here it's sine x plus 2z, and the derivative with respect to z is nothing but 2y. So that's a gradient vector. So if I substitute my point is nothing but 0, 1, 0, right? X equals 0, y equals 1, and z equals 0. If I substitute that in that gradient vector, you get 1, 0, and 2. So that's the gradient vector. Dot my vector. So 0.1 times this 2 over 3, 1 over 3, and minus 2 over 3. Okay, so that's what you get. So if I take the dot product, so this is 2 over 3 times 0.1 minus 4 over 3 times 0.1. So it's minus 2 over 3 times 0.1. So which is, can you tell me what this value is? Oh, okay, so a gradient f, right? So let me, this is gradient f. I substitute, like it's x equals, so this is x. So the point 0, 1, 0. Substitute 0, 1, 0 in this expression, so you'll get this vector 1, 0, 2. Is that clear? So because my point is 0, 1, 0, I'm moving from that point. This is where I am. Okay, well, you get that vector and you're taking the dot product with this 0.1 times u. U is that vector. Okay, so if I compute it, so I'll get, this is minus 2 over 3. So this value turns out to be minus 2 over 3. Okay. Okay, that's why. Okay, so it's quite easy to compute. So we are able to, we don't need to do anything. It's literally all you need to compute is few computations to know what is the change. But if you have to compute, so just imagine computing with hand, right? If I had, so for instance, if I had to compute the exact change, I have to compute the value at f of p and value at f of p plus this point. So when you try to compute them, you'll see that you have to compute all sorts of uh, expressions. You have to compute sines of some numbers, multiply some numbers. So there will be a lot of computation if you want to try to do exact computation. For approximations, it is just literally computing some, this is not so hard. Okay. So let's do one more. So now the function f is this function. So the gradient f would be, if you compute, it is 2x over square root of x squared plus y squared over z squared, 2y over x squared plus y squared plus z squared, 2z over square root of x squared plus y squared plus z squared. Okay, so if I substitute my values in, so 15 squared plus 225, 250, sorry, 254. Okay, so let's see. Something is off. The gradient vector turns out to be, yeah, okay, so the, just let's compute. So 2 squared plus 5 squared plus 15 squared. So this is first of all 4, 10, 30 in the numerator, denominator is 4 plus 25 plus 225, 254. Let's check this. Yeah, okay. I mean, it depends. It's I mean, okay, yeah. So when you write it, it's better to put as arrow over the gradient because to show that it's a vector. If it's not, when you type it, you slightly make this look like a vector. So it's okay. Um, so yeah, when you write it, maybe it's better to put a vector arrow. Okay. So this is the gradient f. So the approximate change is delta f will be the gradient dot this delta r. So the delta r, again in this case, let's compute. Um, it's 0.1 direction in the direction of this. So it's delta r is 0.1 times the direction of this. So that means, so the unit vector would be 3, 6 minus 2 over 3 squared plus 6 squared plus 2 squared. So 36 plus 4, 40, 40 plus 9. So this is 7. Okay, that's a unit vector. So the delta r would be point. So you're moving a distance of 0.1 along this unit vector. So that would be what you get. So this is nothing but 4 over square root 254, 10 over square root 254, 30 over square root 254, dotted with this 0.1 times this. So 0.1 times 3 over 7, 6 over 7, and minus 2 over 7. Okay, so you just compute whatever value you get here. Okay, any questions on this? It's literally compute the gradient, compute the change vector, the vector that you're changing. So that's basically says 0.1 unit in the direction. So you have to compute the unit vector along that direction and then multiply with the magnitude. So you'll get the change vector. And then you'll be able to compute the approximate change. Okay, so that's some information. So you can use derivatives to kind of approximate the values of the function or the approximate changes of the function. So the next thing is some expressions. So this is what are called total differentials or total derivatives. So this is not. So this is basically the symbol df. So you might have seen some things like this in one variable calculus. So df, if it's just a function of one variable, if you recollect, if f is just f of x, so df is the same thing as f prime of x dx. Okay, it's basically literally you write df over dx equals f prime of x, and then you kind of formally take dx to the other side, you get df equals f prime of x dx. So that's what you get if it's one variable. But as I said, in two variables, the df we had a formula like this. So the change in f will be related to change in x and change in y with the partial derivatives. Similarly, the change in f will be related to change in f in x direction, y direction, and the z direction. Okay, so these are formal symbols df. So these are almost like the delta f that we have seen in the previous slide. There's no difference. Instead of the delta, we are writing a d. Okay, so why are they given different names? So we won't discuss that much about this. For you guys, this delta and d are essentially like the similar things. Basically, they are small changes. Okay, so these are supposed to be infinitesimal changes. So if you guys do some physics and other things, you'll see more usage of these kind of stuff. So but for you, you should think delta or d, both of them mean like very small changes in f. Okay, so there's not really much difference. Okay, so let's see this. So there's this problem. where there's a cylindrical can of radius 1 and height 5. So that means there is a cylinder, so radius 1 and height 5. Okay, and so apparently that's what you thought were the radius and the height. You're trying to build, okay, so but it's not exact. So you know that the radius is 1 and the height is 5, but it's not exact. So somehow the radius is off by some number 0.03 and the height is off by some number 0.01. So can you compute the change in the volume? Okay, so what do I do? Right, first of all, can you tell me what is the volume of the cylinder in terms of the height and radius? The volume of the cylinder. So you want to find the volume of the, how much the volume changes. So first you need to know what the formula for the volume is. Right, so it's the area of the circle times the height, right? So the volume would be just the area of the base times the height. That gives you the volume. So the area of the base is the area of the circle, which is pi r squared times h. So that's the volume of the cylinder. Okay, so now can you tell me what dV is, or delta V? The change in volume. Right, you just apply the, yeah, so you apply, it's not the gradient, dV is the change. So yeah, so just compute that. So this is VR dr plus VH dH. So what is VR? VR is nothing but 2 pi r h dr plus VH is nothing but pi r squared dH. Okay, so now let's compute all of them. So we are given all these quantities, just plug them in. So 2 pi, r equals 1, h equals 5, dr is 0.03 plus pi 1, dh is minus 0.01. So this turns out to be approximately 0.6 inch cubed. So each of them are in inches, so this would be approximately 0.63. Just compute this value. Okay. So there's no difference. It's, instead of calling delta, we are now calling it D. Oh, that's there's no difference. You can choose to call whatever you want. So you write. So here it's just that the formula for the function is not given. So you have to write the formula for the function, and then you want to compute the change. Apply the same formula for the dV. So this is the formula for dV. Okay. So that's some information, essentially related to the partial derivatives and the gradient. So, and next, something that we have seen already. So you want to compute tangent planes. So, or if you have the function f of x y equals z, right? So if you have the surface f of x y equals z, this is your surface. Basically, this corresponds to a function of x y z. For every x y, sorry, of x y, for every x y, you write a z, which is given by f of x y. And you want to compute the tangent plane approximation, or the tangent at a point x y. You want to find the tangent plane. By using our formulas before, you'll see that the tangent plane is given by this equation. Okay, so this will be, so z equals, this is z, right? So z equals this will be the equation of the tangent plane if you compute the equation of the tangent plane from the previous stuff that you have done. Okay, so that's why this is called the tangent plane approximation. So and basically you just like we can say that every curve, if you have a one variable function, you can say that the function looks like the tangent line, right? If you have one variable function, if you stay close to the point, there's no difference between, if you zoom in close to the point, there's no difference between the tangent line and the function. They're very close to each other. So similarly, if you take a two variable function, if you have a surface and there's some tangent plane here, if you zoom in close to the function, there's no difference between the tangent plane. They're approximately equal. The value of the function will be approximately equal to the value at the tangent plane. So, uh, so that tangent plane approximation is called the linearization. So the surface can be very curved, but you are approximating using this like flat thing, which is, in the case of one variable, you're approximating it with the line. In the case of two variables, you're approximating with this plane. And in general, in more variables, you can approximate using expressions like this. So it's a higher dimensional version of a plane. So this is the linearization. Okay, so essentially, so geometrically, that is the idea. So we are writing the equations of tangent planes. So, but what is that? So you can see, this is easy to remember. This is like in one variable. So f of x is related to f of x0 plus the derivative times x minus x0, right? That's what you have in one variable. If you remember, f of x will be f of x0 plus f prime of x0 times x minus x0. That's what you get in one variable. But if you have two variables, so you just replace f of x with f of x0 y0, and the derivative times x minus x0 with fx times x minus x0 plus fy times y minus y0, right? This is basically the change in f. This is another way to say is that the change in f is fx times x minus x0 plus fy times y minus y0, right? Instead of writing delta f equals something, I'm writing f equals the function plus something else, right? So all of them are the same formula written in different ways. Instead of writing the function for delta f, I'm writing it as f equals, so delta f is nothing but f of xy minus f of x0 y0, right? So if you use that formula to get the formula for f of xy. So that is what you get. Similarly, in the three variables, the delta f is given by this form, f of xyz minus f of x0 y0 z0 is given by this fx times x, fy times y minus y0, fz times z minus z0. And if I rearrange, I get f of xyz equals f of x0 y0 z0 plus something else. So okay, so these expressions, basically there's no difference between, so the same formula. This is like this, essentially this formula and this formula, all of them are the same formula, okay? So I'm just, they look different, but they are the same for you. You can remember one and you can get everything else. All of them are essentially the same formula. Okay, so so this particular way of writing, it's called the linearization of f. Okay, so you're not just writing about the delta f, you're writing a formula for f. So that formula for f, the approximate formula for f is called the linearization of f. Okay, so but that is an approximation, right? So that's an approximation for the function. But you want to know how good is the approximation. So so it's not exact. That means there will be some error in the approximation. So the error in the approximation can be bounded by some terms like this. So it's error in the approximation. So the actual value is f, and your approximation is this linearization lxy. This formula is called, denoted by lxy. And you want to know what is the difference. The difference between the approximation and f is given by some expression like this. Okay, in the three variables is given by some expression like this. Okay, I do this. Okay, so why is that? So we are not. So it's slightly. I can discuss it if someone wants to talk, but it's not part of the textbook. So it's literally, if you want to find errors, you have to compute things like this. And so we know everything x, x0, y, y0. The only thing that we don't know is this m to compute the error. So the m is nothing but you try to compute these second derivatives, fxx, fyy, and fxy. and you take a bound on that quantities. So that is m. Similarly, in the 3 case, you compute all these second derivatives, fxx, fyy, fzz, fxy, fxz, and fyz. Compute a bound on all these quantities, and that will be m. Okay, so once you know this m, you'll be able to find a bound on the error. Okay, so this is the error and the linearization. Questions on this? So the linearization is this formula, which is essentially the same formula from before, but instead of writing it for delta f, I'm writing it for f by just uh, sending f of x0, y0 to the other side. And but this is not exact, so that will be some error. And I'm saying the error will be, and it can be bounded. It is at most some number like this. These numbers can be computed if you know certain quantities about the function. Okay, so let's see. So can you guys tell me what is the linearization of f of xy here? So first, f of xy is approximately, so this is the formula. So f of x0, y0 plus fx, x minus x0 plus fy, y minus y0. Okay, so this, because f of xy minus f of x0, y0 is this expression. So if I bring that f of x0, y0 to the other side, so you'll get an expression like this. So now let's compute what this is. So f of x0, y0, just plug in f of x0, y0. Let's see what you get. So this is, if you compute, plug these values in, 3 and 2, you'll get 8. Compute fx. If I compute fx at 3, 2, just so compute fx and fy. And so for instance, fx here turns out to be 2x minus y. Fy turns out to be minus x plus y. So if I substitute 3 and 2, you get fx is nothing but 4. So this gives you x minus x0 is 3. Similarly, fy, you'll get, if I substitute, you'll get minus 1 and y minus 2. So that's a linearization. Okay. So this will be, so z or f, so this z equals this will be the equation of the tangent plane, or basically the linearization. Both of them are the same. Okay, so this z equals this is the equation of the tangent plane, and that's why that z f equals that will be called the linearization. Okay, now let's do the second problem. F of x, y, z. The linearization is nothing but f of x0, y0, z0 plus fx times x minus x0, fy times y minus y0 plus fz times z minus z0. Okay, so just substitute 2, 1, 0 in this. So you'll get 2 squared minus 2, which is 2. So f of x, y, z is 2. So what about fx? Can you tell me what fx is? So you can compute fx, and this turns out to be 3. So you get x minus x0 is 2. And fy turns out to be minus 2. Just compute fy. This is a function, right? So just compute the derivative with respect to y. So it turns out to be minus 2, so it's y minus 1. And finally, fz turns out to be 3. So this is 3 times z minus 0. So that's the linearization of this function. Okay. Questions on this? It is literally the same formula that we're using. We have to just, and somehow this expression that we compute is called the linearization. Okay. So this basically, what do you mean by this? So this expression, when we are close to 3 comma 2, is the equation for the tangent plane, and the tangent plane equation will give you approximate values. So for instance, if you want to compute the value of the function at like say 3.1, 3.01 and 2.01 for the first one, you can plug in those values and you get an approximate value. Okay, so then something about the error. So how do you find the error? So that's, so you got, so we got f of xyz is approximately this expression, which is 2 plus 3x minus, this is the same problem from the previous stuff, 3x minus 2 minus 2 times y minus 1 plus 3z. So this is approximate. When you want to know the error, so what is the bound on the error? So the error bound, it turns out to be m over 2 times x minus x whole squared plus y minus y. So let's see. So what is the expression? So sorry, x minus x plus y minus y plus z minus z whole squared. So you compute this. So this will be the error. So this will be the bound on there. So let's compute this. So he's saying x minus 2 is at most. So you want to compute the error of this function given these quantities. So he's saying x minus 2 is this much, y minus 1 is this much, and z is this much. So if I plug that in here, so you get m over 2 times x minus 2 is bounded by 0.01, y minus 0 is bounded by 0.02, z minus z0 is bounded by 0.01 whole squared. Okay, so that's what you get. But what is m? M is supposedly the upper bound. It's the bound on fxx, fyy, and fzz. So let's compute that. So fxx, if you compute in this case, turns out to be just 2. fyy, just compute in this case, is 0. fzz is minus 3 sine z. fxy is minus 1. fxz is 0 and fyz is 0. Okay, so these are all the numbers. So now can you tell me what is the bound on all these numbers? Right, m is the bound on these numbers. So can you tell me what is the bound on these numbers? Guys? Can you tell me what is the maximum value of these, all these stuff, numbers that you see? Oh, can you hear me? Let's see. So 2 is, yeah, so there's 2 here, 0 here, 0 here, 0 here, minus 1 here, but there's minus 3 sine z, right? So yeah, so 3 is one bound if you want, but z is at, okay, yeah, you can say 3 is a bound. That's good, that's fine. But what is the value of this if you, so but z is in between, z is at most 0.01. Right? So z is at most 0.01. So if I plug that in, so you'll get that fzz is at most like, let's see, FZZ is absolute value is 3 sine, is at most 3 sine 0.01. And you see that this is sine 01 is less than 0.01, so this is at most 0.03, right? Because z is not any value. See, z is, we are restricted to these set of values. Okay, so that means that this is less than 0.03. This is so the bound is actually 2. Okay, all of them are at most 2. So just plug 2 in the bounds. So this is 2 over 2 times all these numbers. So 0.04 squared. So if I compute, you'll get something. This is nothing but 0.0016. Yeah, I want a bound. It's like I want the absolute values of all these quantities. Bound means what is the size of it, not the magnitude. I mean, not the sign. Okay. So when this m is basically the absolute values of what is the maximum absolute value you can get. Okay. So that's how you do these problems. Okay. So again, so the linearization is just using those formulas. And then if you want to if someone asks you to compute the error, so this is the formula for the error. This is at most this much, but you want to in the formula there is m missing. You want to find that m. M is basically it comes from the bound. So you compute the second derivatives, all the second derivatives, and you try to see what is the maximum value that you can get for those second derivatives. So for instance, this is 2 here. So these are fixed numbers. So the maximum you can get for these numbers is 2. So but this, so you have to check for this FZZ. FZZ, the maximum you can get if Z is arbitrary number would be 3, but FZZ, Z is bounded to be between at most 0.01. So that's why FZZ would be at most 0.03. So in this list of numbers, the maximum number you get is just 2, right? So 2 is the maximum of these numbers. Like what is the maximum that you can get for these numbers given those constraints? So you plug that number and you get a bound on there. Okay, so yeah, so that's something that's there in the textbook. But yeah, so I didn't tell you why this is the error, where is this formula coming from. So if you want, yeah, if you are interested, come and see me in the office hours. It's not a part of the textbook. It's slightly more, it's not really hard, but it's slightly different. Okay, so that's this chapter. Okay, again, I just want you to understand that all this chapter basically is about this formula. Okay, it's this essential formula. The change in f is given by this formula. So it looks like a lot of information, but all of this are coming from this formula. Different avatars of this, the fact that df equals this, and rearranging it different ways, you can get different stuff. Linearization also follows from this. Chain rule also follows from this. All of them follow from this essential formula. So please try to make sense out of it. Okay. So it's not that easy if you don't think of it. But it's a most fundamental formula. Okay. So okay, questions before I move on? Okay. So delta f or df or f of xy minus f of x0, all of these quantities are the same, right? And this is nothing but fx times x minus x0, fy minus y0. So all of, yeah. Or another way to say it is the gradient times delta r. Okay, so these are all the same expression essentially. And if you divide with the delta of something and take the limit, you will get the chain rule. Okay, So for instance, if we divide with delta t and take the limit as t goes to 0, you get the chain rule. Um, okay, so now let's move on to one more important topic. This is one of the most important topics for practical applications in real life. Why do we care about these derivatives? Why do we care about all these gradients? And right, why do we even want to do all of this stuff? So even in most applied context, this is the reason we study derivatives. So let's see. So you might have seen this in even in one variable, right? So the reason, one of the most important applications of the derivatives is for finding maximum and minimum values. So to optimize certain things. Okay, so optimization problems are really, really important in real life, and you want to find what is the maximum out, given some constraints, what is the maximum, the best we can do, right? So in one variable we study, so if there is just one variable that's we have to maximize over, there's only one x is our input. We can only change one variable, and we want to understand the maximum value of the function. Then we did study those in your calc 1. So we study things like critical points, local extremum, first derivative test, and second derivative test. So please review these stuff. So we'll anyway see. So we're going to do completely similar stuff. So I'm going to talk about them as well. So it's complete generalization of these ideas to higher variables. So in this chapter, we generalize all of this to more variables, say. So for now, just say imagine two variables, f of xy. Okay. So instead of a function which just depends on one quantity, if the function depends on more quantities, how do I maximize that function? Right? In real life, there are too many things that you have to, a certain outcome will depend on, and you want to understand what is the best choice of. So you can think of x, y as the decisions that you make. So what choice of decisions will give me the best outcome? Okay, so let's see. Okay, so if a function f of xy is a function that it's defined on some domain, and you have a point AB, and you want to understand these terms, local and absolute maximum. So this function f of AB is called the local maximum if f of xy AB is like the maximum value in the neighborhood of around that point, the function is the maximum value. Okay, so then it's called the local maximum. But if it is greater than every value in the domain, then it's called absolute maximum. Okay, so if it is greater just in a small disk in a neighborhood of that point, it's called local maximum. If it is greater than every value in the domain, it's called the absolute maximum. It's quite similar to one variable. Similarly, if it is smaller in some small region, it's called local minimum. If it is smaller than every value, it's called absolute minimum. Okay, so this is just, I just wrote it down. So pictorially, what does it mean? So we can see some things like this, right? So local maxima or local minima so local maxima are like the peaks. Okay, they might not be the maximum values. For instance, this value of the function here and this value of the function are the local maxima. And this value of the function here is the local minima, right? So did you guys get this? This is this is completely similar to the one variable functions, right? So in two variables, we have these kind of stuff, right? So these are local maximas. This is for one variable, and this is the local minima. But in like if you have x and y, instead of a curve like this, you'll have a surface for the function, and the local max are these peaks that you see. These are local max, and these values that you see are the local mins. So is that clear? So it's intuitive, right? The local maxes are the peaks. It's just instead of the one variable stuff where we draw these curves, now you'll have a three-dimensional picture. So these are local maxes and these are local mins. And what is the difference between local max and the absolute max? This is absolute, this looks like the absolute maximum, but this is not the absolute maximum. This is absolute maximum. Okay, questions on this? Max are the values around which the function looks close to that point. The function is a maximum value. Both local max and local min means that there is no, that is the maximum value you can get if you look around that point. But if you move in totally globally, that might not be the maximum, right? The peak is just the maximum highest point around that point, but it might not be the highest point. Like you might have to travel somewhere else to find the maximum highest peak. Okay, so that's the notion of local max and local min. So that's quite similar to the stuff that you see in one variable. And then the notion of the critical points. So can you guys tell me what is critical point? Do you guys remember what a critical point is in one variable? Anyone? A critical point in one variable? It need not be max or min, right? So that's the thing. Max or min will be a critical point, but it doesn't mean that it is a critical point. Need not be a max or min. Yeah, so that's what. Good. So critical point are points where either the derivatives are zero. Okay, critical points are points where so there could be, this could be max or it could be min, or it could be something like this, inflection point where the derivative is zero, or it could be something like this, right? So this is a max, this is a min, this is neither. It's like a saddle or inflection, or it could not, it could have no derivative. So that's a critical point, right? So all these things will be critical points. So there's no derivative here, the derivative is zero here, here and here. Okay, so f prime is zero here, f prime is zero here, f prime is zero here, and f prime doesn't exist. Okay, so that's what you have in the case of one variable. Okay, in two variables, it's quite similar. A point in the domain is called a critical point if either the derivatives are zero, fx and fy, the partial derivatives are zero, are both zero, have to be both zero, or the derivatives don't exist. One of them, the derivative doesn't exist. Okay, either something is wrong with the derivative, it is not existing, or if they exist, they have to be both zero. Okay, so that's what you mean by a critical point. So is that clear? So these are points which look different. So just like in one variable, why do we care about these points? These points are, they look different in the, when you look at the graph, these are the points that would look very, very different from the rest of the points. That's why we care about those points. And studying them will tell you a lot about the function. Similarly, even in two, like if you have a surface, instead of this curve for one variable functions, it's the same thing. Either, so a function which has derivative zero or it doesn't exist will look different. So that's why we'll call them critical points. Okay, so why do we care about critical points? Again, so let's see. So can you tell me so if you have a function like this, right? Can you tell me what will be the fx and fy at the max at this points? What will be the derivative, x derivative and y derivative along these points? Anyone? Right, so for instance, you take some max value here, what will be the x derivative and y derivative? Right, So that's the max value. If you move along x or move along y, you'll see the derivative is 0. That's because you can see it. So the geometric way to see it is that you can draw a plane, right? There's a horizontal plane. So the slope along x-axis and the slope along y-axis will be both 0. Not only the slope, okay? The derivative, the slope along x-axis and y-axis, both of them will be 0. Okay, so that's really important. Just like, for instance, in one variable, there's a horizontal line. That's why the slope is 0. That's why the derivative is 0. But in 2 dimensions, you have this plane. That means the slope along x and slope along y, in general, slope along any direction will be 0. Okay, so that's why these are important. Okay, so that's the important information about these functions. So if you have a local extremum, local maximum or minimum, you can see that either the derivatives don't exist. If the derivatives exist, the derivatives will be 0. Okay, so that's what will happen. So if you have the surface, either the derivatives, either there is no tangent plane and there's no derivative. But if there's a derivative, you'll see that the derivative will be both 0. So that's why we care about the critical points. If it is a local extremum, it will definitely be a critical point. Okay, it's quite similar to the one variable. If it's a max or min, it will definitely be a critical point. Okay, so but the point is that it doesn't mean that the critical point has to be a local. It's not the other way. Max or min will be a critical point, but doesn't mean that the critical point will be a max or min, just like we saw here. A max or min will be a critical point, but there could be cases where it need not be a max or min, but it's still a critical point, something like this. So that's something like this, that will happen even in 2 dimensions. So let's see. So for instance, so in this case, you see that there are these horizontal planes. So this is a max, and the derivatives exist, and this is min. So that means this is a nice surface. The derivatives will exist. This is a horizontal plane. So that's why fx and fy equal to 0. So the slope along x-axis and the slope along y-axis, if you compute, so the slope along x-axis and the slope along y-axis, both of them will be 0. Okay, so because of the horizontal. So this is the horizontal. If you look at the function along x-axis or y-axis, you'll see that you'll have a max. So that means fx and fy both are 0. In the same case with the min. It's a local min if you see in both directions. Okay, so these are some examples of critical points. Or what can happen, so these are points where you have horizontal planes, and that's why you can have fx and fy 0, or you can have no derivatives. For instance, here, if you have a surface like this, you can see that there's no derivative. There is no tangent plane, right? So there's a sharp edges, so that you can't draw any tangent plane here. So there's no derivatives. For instance, if I try to move along some axis, the function looks like this. So that means there is no derivative. So the partial derivatives don't exist. So even this, yeah, but so yeah, if it doesn't exist, also you'd call a critical point. So this is also a critical point. Okay. And the third case is that it has a horizontal plane, but it's not, it has a derivative, and the derivative is 0, fx equals 0, and you'll see fy equals 0, but it's not a max or min. So because you'll see that along x-axis, it is, along one axis it's a min, along another axis it's a max. Okay, so you can imagine along one axis it's a min, and along another axis it's a max. So that's why it's not a max or a min. Okay, it increases along one axis and it decreases along another axis. So such a thing is called a saddle. Okay, so that is also a critical point. Is that clear? So these are all pictures of critical points. Either they can be maxes or mins, so hence the derivatives are 0, or you can have sharp points, so the partial derivatives need not exist, or you can have the derivatives equal to 0 but still not max or min. That's because f, it is a max in one direction and it's a min in one direction, so it will, the derivatives will be 0 but still it's not a max or min. Okay, so that's a saddle. So again, so these are the three pictures. So a max will be max in every direction. Okay, so you can see in every direction it will look like a max. A min will be min in every direction. But the saddle, so if I'm not sure if this is clear, so for instance in this direction it's a max, in this direction it's a min. Okay, so but all these points are critical points. These are all critical points. That's because you have fx equals fy equals 0. Okay, all of these points have some special behavior, so that's why we call them critical points. Okay, even if the derivatives exist, you might have behaviors like this. You can have local max, local min, or you can have a saddle like this, or you might not have, the derivatives might not exist. So they might have some sharp points. No, it need not be always at the origin. So you can have it at any point, right? I mean, it's just like one variable. I mean, I drew it at the origin maybe, but you can have it at any point, right? I mean, just shift it. You can get at any point. Okay, so the question now is how do you find these extrema? So just like in one variable, the question is how do you find these extremum values? So it's the first derivative test. It's just completely similar to the one variable stuff. The first derivative test says that if the function has derivatives, that means it has no sharp edges, then you should have the derivatives to be 0 for it to be a max. Okay, so what it's saying is that at max, if the derivatives exist, then the derivatives will be 0. Just for instance here, at a max or a min, if the derivatives exist, the derivatives will be 0. Okay, that's what it's saying. So that's the first derivative test. Okay, so this is exactly similar to one variable. If it is a max or min, you know that the derivative is 0. Okay, so so this basically says that max or min plus fx, fy, if they exist, then they have to be 0. So that's what it means. This is the first derivative test. It's completely similar to the first derivative test in one variable, but now instead of one derivative, you have to take derivative along x and derivative along y as well. Okay, so now let's compute an example. So can you tell me what are the extremum or local extremum values for this function? So what do I do? Right, so if I have if I have my picture, right, I can look at what are, if I know the shape of the graph, I can be able to find. But the point is, if I don't know the shape of the graph, I want to know what are the special points. So for that, so first thing is, can you tell me if the function always has derivatives? Right, fx, fy always exist, right? It's a simple function, right? It's a polynomial. So fx and fy always exist. So can you tell me what fx is? Yeah, so fx is 2x and fy, this compute is 2y minus 4. Okay, so can you tell me the critical points now? Right, so that means fx equals 0 and fy equals 0, which implies 2x equals 0 and 2y minus 4 equals 0. So if I solve, so this means that x equals 0 and y equals 2. right? So the point 0, 2 is a critical point. Okay, so now can you tell me if this is the local extremum value? So this is a candidate for the local extrema value, right? So will this be a local extrema value? Okay, so it's not clear. It could happen, like it could be any of the shapes, right? It could be a maxima, minima, it may not be nothing. All we know is that its derivatives are 0. It could be any of these 3 cases. So how do you distinguish between these 3 cases? Uh, no, I mean, yeah, so you want to do like something like a second derivative test, but we do, okay, so that's the next, I'll come back to that, but you'll just look at this, okay? F of xy, I can write, can you notice that this is x minus 2 whole squared plus y squared plus 5, okay? I can rewrite, yeah, so you can try to see how the function looks around that point, 0, 2. Okay, sorry, this is, something is off here. This is x squared. This is x squared plus y minus 2 whole squared plus 5. Okay, so just this is the same function as this. Okay, just I rewrote, completed the squares, and I got that f of xy is this. So can you tell me from that, what can you tell me? So the, 2y minus 4. 2y minus 4. Oh, the 5 came from, okay, I just completed the square. So x squared plus y squared minus 4y plus 4 plus 5, right? This is 4 plus 5. 9 is 4 plus 5. And y squared minus 4y plus 4 is y minus 2 whole squared. Oh yeah, it's something related to the circle. But what I'm trying to say is that the value of the function, what will be the minimum value of this function? Right? The minimum value is 5. This is greater than or equal to 5 always, right? And the value of the function at 0, 2 is what? Is also 5. Okay, that means that 0, 2 is the minimum value. Okay, so 0, 2 is a minimum value. Is a minimum. Okay, so is that clear? So I just knew that these are the candidates, but it's not enough to know that they're the candidates. We have to show that, okay, somehow at those candidates are really the maxima or the minima. Okay, so so just from the first derivative test or the first derivative, we can know the candidates, but it's not easy to know that they are the maxima or minima. So you have to use extra information. So for instance, in this case, I computed the value of the function and it turned out to be 5, and I showed that the value of the function is always greater than or equal to 5. It's some other extra information that I'm telling you about the function, so that I know that the value of this is the minimum of the function. Okay, so this is something that's extra. This is from the first derivative test, so that you know that this is in fact the minimum value. Okay, so that's how you compute the local estimate. So let me do it for this function, some other function here. So can you tell me what are the extrema? So what are the critical points? Yeah, so you can do charts, but you have to, I mean, like, how do you should make sure that you can draw the charts properly, right? So you have to draw how this function looks. It's not enough to see that it's nice along x and y. So that's the problem. You have to see it along every direction. Okay, right? It might be nice in two directions, but in a third direction, it might not be nice. So that's why you have to be careful. So it's not just do it in X and do it along Y. Okay, so let me quickly finish this and then, okay, so I'll take 1 minute. So can you guys tell me the critical points here? So fx is minus 2x, fy is my 2y. So that means 2x equals 0, 2y equals 0. So 0, 0 is the critical point. So can you tell me if it is a max or min? Or neither? Yeah, it's neither. Okay. In fact, it's a saddle. Okay. Slash. Okay. So just you can verify that because you can see that along x-axis, along y-axis. So along y-axis, the function is f of 0y is y squared. So that means it's a min, right? Along y-axis, it's a min. And along x-axis, the function is f of x comma 0. You'll see that it is a max, right? Which is minus x squared. So along x-axis, it's a max. Along y-axis, it's a min. So that's why it's not a max or min. So it is a saddle. Is that clear? So for instance, so Brian, you were asking me something, right? So it's not enough to show that it is a max or min in both the directions, but if you can show that it's max in one direction and min in one direction, we know that it's not a max or min. So we can use what you said to show that it's not a max or min, but not to show that it's a max or min. Okay, so so in this case, you have it's a max in one direction and a min in one direction, so it's neither. Okay, so so that's something, but if you remember in your Calc 1, so we after doing the first derivative test, we also do a second derivative test. So we have these candidates, but we want to know what type of a critical point it is. Right now, we are using some ad hoc techniques to know what kind of a critical point it is. But if you want to use more information about the function, we'll be able to use second derivatives to compute know the information about this function. So we'll discuss that. So the next thing is about a second derivative test. So we'll discuss this in the next class. Okay. So I'm done for today. So if you have any questions, stay around and ask me questions, please.